Okay, in the last video, we discussed the concepts of first and second order structures. And here in this video, we start with measuring first and second order structure. Um, for the first order structure, intensity of the event in space varies from one place to another. And this intensity is decided by a function or a phenomenon, right? We mentioned this in the last video. And generally, there are three categories of methods to quantify or say to measure first order structure. There are crude density estimate, quadrant count methods, or kernel density estimation. So here I'm providing a very simple example for counting events in quadrants. The feature, the special part of first order structure is that the intensity of events varies across space, right? So the simplest way to address this structure is dividing the whole space into small cells, right? We have 1, 2, 3, 4, 5. 5 by 1, 2, 3, 4, 5. 5 by 5, 25 quadrants in this space. And each small black cross here represents a specific event, right? So in this whole space, for each cell, within each cell, there is a different number of events, right? And here, the values here, they're representing the events, the number of events in each quadrant. And since each cell has the same size, let's just say that size is 1 unit. Here, these values, they are also representing the event intensity or say density in each quadrant, right? So here, obviously, the intensity of the events changes, or you can say varies across the space. That is a phenomenon without any context. If we give it a specific context, say that each event is actually a building. So it means that there are different numbers of buildings across the space, right? Why? What's the function controlling, manipulating the intensity globally within this space? Well, we can say urbanization, right? If there is urbanization, there must be downtown in several years or in decades, and then there are suburbs surrounding the surrounding the downtown, right? Then if you go further away, there is rural area, right? So this is very typical, right? All those cells with high intensity of buildings, high density of buildings, they are representing what? Downtown area. And surrounding areas with less than intensity, suburbs. And then those areas, or you can say those cells, with very limited number of buildings or no buildings, they are rural area, right? So first order structure addresses global spatial configuration, or you can say global spatial structure, okay? And here is another more advanced method to use randomly distributed quadrants. Say we have this, obviously this is a city, right? This is a city. And we have this study area with very solid black line, right? And inside this study area, we have multiple small quadrants addressed by what? By gray boundaries, right? If you want to know more detail, please go to this website. But it's a quadrant count using regular and random squares, okay? And how about second order, right? First order is about global trend, the global spatial trend. Second order, summary statistic describing spatial dependence. The special part about second order is that locations of events are affected by locations of other events, or simply locations of events are affected by other events, right? Typical methods include mean nearest neighbor distance and a lot of other distance functions, g function, f function, and k function. So here I will go deep a little bit for k function, cumulative frequency distribution of the number of events within critical distance of each event. So here I think the tricky part is called critical distance. It's you can consider this critical distance as a searching area, or let's just use distance to represent this searching area. Searching radii. The example be like this. For each event, for example, in this figure, this gray event here is the main character, is the center, right? We search its neighborhood using concentric circles. Each circle is, of course, each circle addresses a specific searching area with a specific searching radius. So we have 1, 2, 3, 4, 5. 5 concentric circles, 5 radii. Of course, as this radius increases, more and more events can be covered by your searching area, right? So the function's idea is simple. We create a scatter plot, or you can say a figure, a diagram, between what? Between R. R is the searching radius. And K. K is simple. The number of events included in your searching area. 1 R increases. Okay. Obviously, this positive relationship is easy to understand because the larger your searching radius is, more events should be included in your searching area, right? But I mean, this relationship, positive correlation, is not linear. At the very beginning, for example, from 0 to 10 units R, okay, you can see that as the R increases, I mean, more events are included in your searching area for sure, but the speed is pretty low. It means that, okay, the searching efficiency is low. The slope is also low, right? It's very flat. It means that there is what? There is scattering effect. Remember the spatial distribution of second order structure. There are clusters. If you cluster 1, cluster 2, maybe cluster 3 here, cluster 4. So when you start searching at the very beginning, I mean, this is the starting point of the searching, right? If you begin to search, maybe when the radius is 10 units, right? You have covered all other points surrounding you, surrounding this starting point. Then when you increase R continuously, and you can see that more and more events are included, and the speed of finding new events also increases because the slope of this curve increases dramatically. From 0 to 10, maybe less than 200 or 300 events have been found, but within the same 10 unit distance, from 40 to 50. 40 is somewhere here. Let's just say maybe 4,500 events here. But at 50, there is about 10,000 events. So within these 10 units, how many events were found? From 45 to 10,000. That's 55,000. Oh, sorry. From 4,500 to 10,000, right? That's 5,500. Yeah, 5,500. But how about the increase of events from 0 to 10? It's from 0 to maybe 2 or 300. So you can say that speed increased a lot when you increase the radius. So what's the meaning of the solid black line dashed red line and this shaded area? So the KOBS, which is addressed by black solid line, that's the observed curve for this searching for this specific situation, right? And K thel, which is addressed by red dash line, that's the theoretical increase of KR, which is the number of cases or number of events as the R increases. So black dash line, that's observed phenomenon. Red dash line, that's theoretical curve, okay? This shaded area, that is pretty important to us. That's the envelope created by a lot of simulations. The upper boundary is KHI, which means K high. The lower boundary of this shaded area is called KLO or K low. It means that in order to simulate this phenomenon, this searching, maybe hundreds or even thousands of simulations have been done, and all the curves from the simulation, they form this shaded area. It's an envelope with an upper limit and a lower limit, and you can see that the theoretical curve is in the center of this envelope, and this specific observation for this specific spatial distribution of points, a part of it is outside of the envelope, which is what does it mean? It means that it is beyond our expectation. When the radius is low, you can say there is a segment of this black solid line or curve. It is outside of this boundary. But for most part of this black curve, the observed curve is well inside this envelope, which means that our simulations, all those simulations, maybe hundreds or thousands of them, they are effective because together they can be used to form this envelope to include an observed phenomenon. Okay, so this is a strong suit for simulation. We run thousands, we run many times. You will say how many is many? Is many enough? Well, it depends on your specific application. There is no so-called correct answer. This many could be dozens, could be hundreds, could be thousands or millions. Okay, but the idea of simulation has been addressed here. We run a simulation model for many times to form an envelope and say if the observed phenomenon is inside this envelope. And of course, we also need to know if the theoretical curve or theoretical phenomenon is inside this envelope. Okay, so this is K function, but let's get back to K function. It is used to address the second order structure, and if the observed pattern curve is just like this black curve is inside this envelope, then we say there is second order structure within your study area. Okay, and then let's talk about using null models to evaluate patterns. So how much does an observed pattern deviate from null? And the null here is CSR. I mentioned this concept at the very beginning of the second chapter. It's called complete spatial randomness. I will go deep with this concept later, but now I can give you some information. CSR is something special. It's a special spatial pattern that does not have first order, neither second order, which means if it is a CSR, it's a pure random spatial distribution of events. There is no second order, no first order. Okay, now let's just say CSR is a common but simple null model. right? If we want to evaluate a specific pattern and say how much does that pattern deviate from CSR, what should we do? What should we do uh, with a simulation model to judge uh, if a pattern is following CSR or not? If not, how much does it deviate from CSR? So a general approach is called a Monte Carlo simulation. So repeated random sampling from a probability distribution to obtain numerical results. This method has been widely used in different disciplines, different sciences, okay? So in our case, simulate patterns using random realizations of the process given a null model, for example, CSR, and compare observed pattern to the simulated distribution. This is it, right? This is actually Monte Carlo method. We run a model many times to form this shaded area, in other words, this envelope. Then we make a curve for the observed specific pattern you care about, and say if this curve is inside this envelope. If yes, then we say, okay, at least this specific pattern is not deviating very far away from, or it's safe to say that this pattern is not deviating from CSR. If your black curve here is outside of this envelope, then you should say that, okay, this observed pattern is just not CSR or the null model you are interested in. Okay, so compare solid curve with this envelope. Of course, you will say, how can I decide the boundaries of the envelope? If I run the model for 10,000 times, maybe there are curves outside one of the, or you can say a lot of results of simulations. They formed curves, I mean, even higher than this K high. How should I decide which one of them should be the upper boundary and lower boundary? Again, there is no specific answer for that. It depends on your tolerance, right? Depends on your specific application. But the idea of Monte Carlo method is here, okay? Run a simulation multiple times, form an envelope, and compare the observed curve and the envelope, okay? Yep, Monte Carlo method here. Okay, here is another example, right? Here, in figure A, we have the observed pattern. B, I mean, we have run n times of the simulation to form n curves. These n curves, they are going to form an envelope. And here n is 999. Okay, n is equal to 999. Okay, then we compare this observed one and the observed curve and the envelope formed by this 999 simulations, right? So solid black line observed. Again, in the center of this envelope, we have a dashed line that is for the theoretical curve for this pattern, and the shaded area simulations envelope, right? I mean, this black curve looks like on the boundary of the upper boundary of this envelope, but according to this explanation from the textbook, right? Say this is say, right? This is say the simulations compared to the observed data, right? Shaded area compared to the black solid curve. In this case, the observed patterns K function lies outside. Yeah, if it says lies outside, we'll just accept that because it's a text. It's a conclusion from the text. So here we can say that this pattern is observed pattern is deviating far away from what? From second order pattern or second order structure. This is not CSR because we're using K function. It's for addressing second order pattern. So yeah, here we have the results. We did simulations multiple times to form the shaded area, and the observed curve is outside of this shaded area. Then, okay, we compared them. The conclusion is that this specific observed pattern is not with second order structure. Okay, so the complex part is what? Is creating the simulation model and run it for a specific time, Okay, now let's talk about CSR in detail. Complete spatial randomness, CSR. Or it has another name, it's called homogeneous spatial Poisson distribution, okay? Events are occurring independently, right? Which means that there is no second order, because if there was second order, all events, they should affect each other's locations. It means they are not independent, but here events are occurring independently. And secondly, the probability that an event occurs in a given length of time does not change through time. It means that there is a specific value. Usually, we're using intensity. Okay, lambda here. Homogeneous spatial Poisson process with one parameter, and it is a constant here. Okay, so events are uniformly, which means there is no first order. There is no background function manipulating how can I say, manipulating the spatial distribution of all those dots, which means there is no first order structure, and independently, the location of one event does not affected by any other event's location, which means there is no second order. Okay, so CSR is always used as a null model because it's so spatial. It's completely random. That's the reason why it's called complete spatial randomness. Okay, so this is CSR. And it can be simulated by drawing an XY coordinate pair for each event from a uniform distribution. A uniform distribution has another name. Sorry, I'll just stop here. Okay, I'm not going to make you more confused. Let's just say, remember this. How do you form a CSR? Firstly, you have to find out a uniform distribution. What is a uniform distribution? It means that the probability of picking a specific value from a pool stays the same, which means each possible value has the same probability to be picked from the pool. Okay, you can have a huge pool or small pool, but yeah, that's it. The probability is the same for each possible value in this pool. Okay. Okay. Here is another model from the NetLogo I mentioned before. That zip file for base models. From the textbook, right? So here is a very simple simulation for forming CSR across a space. Okay, I'm not going to detail it. I suggest going to NetLogo and play with it a little bit. Okay, I will just stop the recording from the for this video, and I will see you in the next video. Thank you.